Okay, so as a reminder, we're trying to analyze the monkey hunter problem, and we've drawn a picture. We've taken components of any vector quantities, and we wrote down our equations of projectile motion. So now we just need to write down what we know and what we don't know. So starting with the first equation, delta x, v0 x, t, etc., delta x. So let's change the color. I don't like this color. So delta x is the horizontal range, and oh, wait a second. What are we analyzing? We're analyzing the motion of the bullet to see where the bullet goes, right? So we didn't even think about what we're analyzing. We just started writing things down, which is good. But now let's think about what we're analyzing. We're analyzing the motion of where the bullet is going, right? So the bullet is going to go like that. And we want to know if the bullet will hit the monkey. So how do we figure out if the bullet will hit the monkey? You might just pause and think about for a second how we figure that out. But I'll tell you the answer now. What we want to know is when the bullet reaches this position here, we want to know once the bullet gets that horizontal range, where is it vertically? So we want to know where the bullet is vertically when it reaches that horizontal range. So we're first analyzing the motion of the bullet, and then we have to analyze the motion of the monkey and ask, where is the monkey at the time that the bullet has reached that horizontal range? Maybe the monkey's down here. Maybe the monkey's up here. Actually, there's no reason the monkey would be up because it's not jumping. He's just falling. So we actually have to analyze both motions, the bullet and the monkey. We've got two objects. We're going to analyze them both. Okay, so what we're asking here is when the bullet goes plus 100 meters, because to the right was positive, and the bullet has an initial velocity of v0x. We can look back and see v0x is, careful. To the right is positive, and the x component of v0 is in the right direction, so that's plus 49 meters per second. T, do we know the time? We do not know the amount of time it takes to get there. That might be an intermediate thing that we need to know. Delta y, that's what we need to find out, right? That's the thing that we need to know, is where is the bullet when it has traveled 100 meters to the right. So that's the thing that you need to figure out, is that we are asking when the bullet has moved 100 meters to the right, where is it vertically? That's going to help answer the question. A sub y for the bullet is, again, we've chosen up as the positive direction, and acceleration is down, so we look at those arrows, and the acceleration is minus 9.8 meters per second squared. T v0y is, again, v0y is up, and we've chosen the y direction as up, so that's positive. Oops, what's the number? The number is, it was 9.8 plus 9, equals plus 9.8 meters per second. That was just coincidental. It had the same number. And Vy final, we don't know. And I'll tell you, you might see that's not relevant to this problem. But let's see. How many variables do we have? So there's 7. There's always, for projectile motion, 7 either knowns or unknowns. So I always count them to make sure I haven't forgotten any. There's 7 of those. Okay, so what do we want to do? We want to solve for delta y. So we want to solve for delta y. And so delta y is equal to 1/2 a sub y, 9.8. I'm going to leave off a sub y is minus 9.8. Leave off the units because I haven't left myself a lot of space. But everything is MKS, so I feel okay with that. 9.8 T. I think I plugged that in right. And so we need to know T. So we need to go to a second equation to figure out T. So I'm going to use that one. And delta x plus 100 meters equals v0x plus 49. I guess I was leaving off units, times T. Therefore, T is equal to 2.04 seconds. Plug that back into delta y. Therefore, delta y is equal to, and I'm not going to write it out again. Let's just go ahead and multiply it out. Okay, so now I'm in a little bit of a quandary because what I find is that the bullet falls negative 0.4 meters. What does that mean? That means that the projectile motion that I've showed here is actually a little bit off. And maybe I made some bad choices, right? So, because what that means is that once the bullet has traveled 100 meters over, it's going to be below the x-axis. It's going to be down here, right? And if I started at the ground, then it's already going to be on the ground. So the bullet is basically, I made the bullet too slow. Now, maybe I could argue that the hunter is, I could argue, absolutely, that the hunter is taller than 0.4 meters. The hunter is holding the gun. So there is, and this is a complication that's not necessary for this problem, but there is this further space to the ground. And so it is, the bullet is 0.4 meters below where it started, but it hasn't reached the ground yet. I guess that's okay. The other thing I could do is say, ooh, I chose too slow a bullet speed. It was not really a good order of magnitude sort of problem. I should have chosen something more realistic for a bullet, like 100 meters per second, 200 meters per second, 500 meters per second, something that I could look up. But if it was a beanbag gun or something, maybe 50 meters per second is reasonable, anyway, whatever, something that's not really a gun. But let's just say that for the sake of solving this problem, that the bullet is indeed 0.4 meters below where it started, but it's still falling. It hasn't hit the ground yet. We could go back and change the initial velocity of the gun so that it follows that original trajectory, but that's fine where we are. Okay, so delta y equals 0.4 meters. So now what do we do? Well, remember, we want to find out if the bullet hits the monkey, right? X marks the spot. Oh, poor monkey. Does the bullet hit the monkey? Well, so we need to know where the monkey is at the time that the bullet passes the plane, right? The plane where the monkey is. We need to know where the monkey is. So we need to write down the equations of motion of the monkey. Well, the monkey is actually just moving in one dimension, right? So the monkey, here's the monkey, and it is falling with an initial velocity of 0, an acceleration of 9.8 meters per second squared, and we need to know how far the monkey has fallen. And what else do we know? We know the amount of time that it takes the bullet to get to that, to the level of the monkey, to the plane of the monkey. And so we actually know that delta t, or t, I go back and forth between t and delta t, but it should be t. T is 2.04 seconds. So we can write down the equation of motion for the monkey, 1/2 at squared. And it's one-dimensional, so the monkey is moving in one-dimensional motion, so I'm not going to bother with the subscripts. We only need that first equation, so we don't have to write down the other two, because all we need to know for the monkey is delta y. Oh, let's choose a positive direction for the monkey. You might, just to be consistent, choose the same positive direction. You don't have to. We can choose this as the positive direction for the monkey. Delta y is equal to 1/2 positive 9.8 meters per second squared times plus 2.04 seconds squared plus 0 times 2.04 seconds. Okay, so the monkey's displacement is plus 20.4 meters. Okay, so the monkey displaces 20.4 meters. Okay, so does the bullet hit the monkey? So does the bullet hit the monkey? You might say, oh wait, the monkey displaces 20.4 meters and the bullet displaces 0.4 meters, so no, the bullet doesn't hit the monkey. But if you do say that, you're not thinking about the fact that they start at different places. The bullet goes 0.4 meters below where it starts. The monkey goes 20.4 meters below where it starts. And indeed, they're in the same place at the same time. X marks the spot. Boom. Poor monkey. So we found, given the choice of speeds for the projectile, that we do have to choose a projectile shooter that shoots fast enough so the bullet will actually reach the plane of the monkey before it hits the ground.